Hello and welcome to day 15 of the Advent of Code 2021. Yesterday I had to travel and so I couldn't spend much time on the problem. And unfortunately I did a big mistake in part one that made it work in any case with the input, but actually it's a conceptual problem that will make it very hard to solve part two. Let's see what happened yesterday. The problem was a path finding problem. We have to calculate the shortest path in a grid where every cell of the grid has a cost, which is the cost to cross it, which means that the shortest path is not just the geometrical shortest path, but the one that minimizes the cost of every cell that we have to touch. What I did was to implement a breadth first search. So let's see an example with a graphical representation. So what I do is, first of all, I have a starting edge, which is essentially a set of cells. Let's say this is the starting edge. At every iteration of my algorithm, I find the set of cells that are adjacent to the one that I'm trying to process. So in this case, this is the edge, it's only one cell. So in the next iteration, I will mark this as processed and find all the corresponding cells. So this, and this, all the cells that are neighbors of the current one. This is the new edge. I will calculate the cost of all of them, which is easy because I knew the cost from the starting point. So all their cost will be the cost of a starting point plus their own cost as a cell. So that the cost I calculate is the cost to reach them. So I calculate the new edge, so they get old, and I calculate the new edge, which is the cost of all the cells that are around the ones that I'm exploring at the moment. And then basically at every interaction of my algorithm, I expand the edge, I find the new edge, so all the cells that are neighbors of the previous ones, and calculate their cost, so the cost to reach them from the starting point, as the cost of the neighbor that I already knew, plus their own cost as a cell. And at that point, when I find finally the ending point, so when I reach the end, I just have the cost that I had to reach that specific point, starting from the initial edge. Now this works, and in fact it worked for the part one and for a sample input of part two, but it has a big problem. So let's look at this chart. Let's say that this is the starting point and this is the end point. So we have to cross the chart. And let's say that the green cells have a cost of 1, and the red cells, these ones, have a cost of 2 or 3, or in any case higher than the cost of the green cells. Now, intuitively, you know that the best path, the one that minimizes the cost, is not the one going in this direction, just crossing the whole thing, but is the one doing this. So the shortest path in a geometrical sense is not the best solution in a cost minimization sense, because you want to take a longer route to avoid a costly part of the chart. And to do that, you need to be able to move not necessarily in the same direction, but always like this, in diagonal. But you need to be able to do, for example, this. You need to be able to do to go in every direction. And that is something that my algorithm is not really doing. So what we have to do is we have to implement Dijkstra. So let's look at the part 2 of the problem. This is very tricky because the sample input, the one that the problem gives us in here, doesn't need that kind of consideration. So it works with my algorithm. So my algorithm worked on the part 2 as well for the sample input. But when I gave it the real input of the problem, so this big thing here, it didn't work. And since the size of the input is huge, it took me some time to troubleshoot. But once I did, I found how stupid was my original idea. So let's do something smarter now. Let's try to implement it in a more proper way. So first, let's see what part 2 is asking. I find that's quite annoying. It's not very interesting as a problem. what it's asking us to do is to expand the cells, to repeat the metrics. So this is the input, for example, the input of the problem, and we have to repeat it. So here, this this grid, that in the case of the sample input is 10 by 10, but in reality is much bigger, is repeated 5 times in vertical and horizontal. But every time it's repeated, we increase every value in the grid of 1, both in horizontal and vertical. And when the value reaches 9, we reset it back to 1. So we have to do a modulo. And this is something I already implemented here. So I don't think it's worth much explanation. The problem is relatively simple to do, this replication operation. It's just very annoying to implement this modulo and to understand exactly what the problem is asking. That took me some time. But the operation is simple. So I just have tx and ty, where t stands for tile, because I assume that the whole grid is like a tile that is repeated to form a tile map, essentially. So tx and ty go from 0 to 5, because we have 5 repetitions. That's what the problem states. And we simply create a new value, which is the original value of a cell plus the tile coordinates, so the numbers between 0 and 5. We sum them, and then we have to do this modulo operation. But since the computer does the modulo starting from 0, so modulo 9 is 0, and the problem is asking us to reset to 1, we have to do this trick. We remove 1, we do the modulo with 9, and then we add 1 back. So basically we shift everything to count like humans, from 1 to 9, not from 0 to 8. And we put that in a cell. So this operation, this expand cells, is simply calculating the expanded, multiplied input of the problem. And at this point, part 2 is simply expanding the cells, you see here, and then invoking part 1, because then the problem is exactly the same. Part 1 is where the search of the optimal path happens, and this is a part that actually is not working. So if I run it on my input, I copy the input from the problem, you see that the value of part 2 is 315, which is, ironically, I mean, not that ironically, what exactly the input is asking. So the problem, the code, the website expects that value, which is the one that we get. But this happens because if you look at this path, this always goes downward and rightward. So it's never doing any movement that is not consistent with this kind of pattern. So it works. But in our input, in the real input, the real problem, we do have sometimes a path that goes upward or leftward. So it's a bit more complicated. So we have to implement an algorithm called Dijkstra. I like it because it's a really nice name that you learn in every computer science class. On Wikipedia, you can find a complete description. And I can also suggest a website called Rosetta Code, in case you are interested in to look at the implementation. Let's see if I can find it. So Rosetta Code is a website in which you can find implementation of a lot of problems in a lot of different languages. So let's look for Dijkstra. It's very simple name. For Dijkstra, you can find the implementation in, you see, a lot of different languages. I find this implementation is a bit long because we're using already a sparse representation, but that's fine. It's there if you want to see it. But I'm going now to just implement it from scratch. So let's see. I have this part 1, which is where the error is. And what I'm going to do is I'm going to re-implement part 1. So this I call part 1 old. And then I create a new part 1, which is where the magic will happen. I'm sorry for my voice. It's even worse than usual because I'm have a bit of a cold. And also I changed my headphones because I'm traveling, so I'm not using the usual ones, but Bluetooth ones. So let's see how it works. So first of all, we need from part one, we get the max coordinates. This doesn't change. Then we again have a result, which is the total risk, which is exactly the same as we did before. So we have essentially the cost associated with every cell. Then we have the set. Thank you, Harley Davidson. Then we have the set of the cells that we want to explore. This is what we call the edge. But now that we are trying to implement Dijkstra, there is a big twist, which is that this is not anymore a list of cells without any particular consideration, but is a queue. So we want always to explore the closest cell, the one with the minimum cost. So essentially, the Dijkstra is very careful. At every step, it tries to look for the cell that is the shortest that we know, the closest that we know, and explores from that point. So what we create is a what do we call it? To explore, let's call it, because that's what it is, which is a priority queue. What the hell is a priority queue? Is, first of all, I have to import it. It is, if I remember correctly, in queue. So from queue import priority queue, yes. What is a priority queue? A priority queue works pretty much as a list. So it keeps a list of elements, but it also takes care automatically of ordering them according to some value, some priority, so that you can always get the element with the highest or lowest priority. In this case, the priority is the distance. So every time we insert an element in the priority queue, we keep track of the distance from the starting point. And when we explore a new element from this set, we take the one with the lowest distance that we know. At that point, we are sure that it doesn't matter when we inserted it, so we're not exploring in waves, but we explore one by one, starting always from the closest point. Doesn't matter if it's something that we just added or it was there from before. So we always explore from the closest point. What does it contain to explore? As we did before, it starts with the starting point. So to explore, we have the method put. Put wants an element. The element is basically the thing that is in the queue. As a convention, this is something that you find already in documentation. This can be easily a tuple where the first element is the priority, in this case 0. The priority in our case is the distance, the total distance from the starting point. The first element is the priority, so 0, the distance, and the second element is the starting point, so 0, 0. Notice that when you sort tuples, the first element is sorted first, so Python automatically knows that this has to be the criteria to sort, which is exactly what we want. And now the implementation asks us to keep exploring, so keep getting the closest cell, the one that has the lowest priority, so the one with the closest distance, and explore it and see what we can reach from that. So we have to go forward, and as long as we find elements to explore. So what I say is while to explore is greater than 0, I think to explore has no length. My editor is not telling me. To explore is a queue, and for whatever reason in Python, the queue do not have. You cannot do the len operation. You cannot get the len. Well, let's pretend we don't know. So sorry. So let's pretend I don't know. I just run the code, run it, and I see that it complains that priority queue has no len. What we have to do, I think there is a thing called queue size, which is the approximate size. Very annoying. I don't know why it has a different name from everything. But it's not reliable because this queue can do also some, what to say, multi-threading operations. And I think there is an empty, yes. So, there is also not empty. Nice. Okay, I didn't know. Is it actually working? Yes. weird. I never saw this not empty thing. Okay, this is not really working. So we have to say that as long as the to explore, which is the list of nodes that we still have to investigate, is not empty, we have to investigate. How do we investigate? First, we get the shortest, the closest element. So the one that we are sure we can reach with the lowest cost at all. Why we start from it? Because we know that we may have different paths to reach the same cell. And since every cost is positive, we know that the shortest, the closest element we have is for sure the one that we can already know for sure how to reach with the shortest path. For the others, it's possible that now that we have the closest element, we find some better, smarter way to reach other elements passing by this shortest one. So it's better to explore from the shortest element because we may find shortcuts to reach other elements that we already know, but we know with a suboptimal distance. This is much easier if you look at examples. I probably put a link in the description so that you can you can see live how it works. So now I simply unpack what I just put here. So the cost and the coordinates. They are equal to what? To this to explore dot no, there is no pop. It's called get for some reason. It's a strange name because get suggests that I'm just getting an element, but it's actually getting the element and removing it. So this is doing two operations: is retrieving the highest priority element in the queue, which is the cost, but also giving me the value itself, so the cost and x and y of this cell. This is the best. This is our solution. Now that we found it, we want to ignore it in case it was already examined. So if x, y in total risk, sorry, continue. Why this? Because well, this shouldn't be necessary. No, in fact, we can skip it at all. Never mind. I was thinking that it's possible that the algorithm in the later iteration will try to add it again, but not because we are going to implement it in a nicer way. So we get the closest element, and we know for sure that this can be put in the total risk. So we just say that total risk for x and y is equal to the cost. So now we found an element that was the shortest. We know that for sure that this element has this distance from the starting point, and we just put it in the list. Then we have to explore the neighbors, and this is the same operation we had before. So this operation, I just copy paste. So I'm simply iterating over all the neighbors of this specific node, so not of every cell, but of this specific node, which is the shortest. I take the 4 elements that are up, down, left, and right. For each one, I check that they exist, and they're not already explored. If they're not, what I do is I put them in the list of elements to explore. This condition, this not in total risk, is the reason I didn't put any check on the fact that node we're getting is not in total risk, because I'm checking later. So before adding, I know that this element is completely new. So to explore, what I do, I put this new element. It has the same structure. So the first element is the cost, and the cost we know that is what we already had. So the cost to reach this specific node we are exploring, plus the cost of this same cell. So the cells at position and x and y. This is the cost, and then I have to put the coordinates, of course, and x and y. So I put in back the same structure. The first element of this tuple we put in the queue is the cost, and the second one is the coordinate of the cell. And this continues. Every time it takes the closest node. Doesn't matter in which wave we added it because it's a priority queue, so it prioritizes the cost to reach a node compared to when the node was added to the queue, which is exactly what we want. And this goes on as long as we have something to explore. And at the end, we simply finish it. We explored everything. The while is out, and we have to return what the total risk of the cell that is at the end, which is max x and max y. This is something that we had already in the first part of the problem. And now if I run, I should see a solution. Yes. This solution is wrong because I'm not checking the total risk. So if x and y is in total risk, I have to stop because there is some duplication. So if x, y in total risk, we continue. We skip it. Yes, this is the solution. And this is the solution of the problem. I'll put it in the repository, also put in the description some links to help you understand. This is very abstract, so don't be worried if you don't get everything. See you next time. Bye.